In this video, I'd like to talk about operators and the Heisenberg uncertainty principle in quantum mechanics. It's quite easy to get lost in the forest and just start hearing words that mean absolutely nothing once you get a few weeks into your quantum mechanics class in school. And so I'm making this video because I hope people can take away something from it. Even if you don't know anything about quantum mechanics, I'll try to keep it as understandable as possible. And I'd also like to preface by saying that one of the professors in the College of Chemistry at Berkeley recently said something that meant a lot to me, and that was scientists and engineers have an obligation to the public and to others to teach people and show them and keep them informed and try to not speak on such a high level that we completely lose everyone else. And it meant a lot to me, and I think part of the reason why I want to make all these videos is because I hope that we can at least have the more people involved in the discussion and what kind of problems the world's facing, and once you get down to the minutia of science or any discipline, what's it like on the day-to-day basis and how you struggle and fight through it. So hopefully this video is helpful to people. If you're just interested in quantum mechanics, it's from what I've seen so far, it's a really cool subject. Even though I'm chemical engineering, it is a very cool discipline in science, and I hope this makes some other people interested in it as well. So to begin with, the best way to approach quantum mechanics is to understand that once we try to model the behavior of electrons, everything we've used before breaks down, because the mass is small enough that their de Broglie wavelengths are no longer negligible. And consequently, the electrons will take on, they'll essentially behave randomly. If we look at a single electron and what it does, we cannot predict what it will do. And because of that, we need to, instead of, like in classical mechanics, where we could say, I know that this pen falling from A to B will take X number of seconds, I know the exact path it will travel, I know the exact velocity it will have when it hits the ground, we can no longer use any of that stuff. Instead, what we have to use are averages. And so statistics and calculus plays a huge role in quantum mechanics, and that, I think, is a big reason why it's considered a high-level discipline in science that is a difficult thing to understand unless you have a good background in calculus and statistics. So I'll try to phrase this in such a way that if you don't necessarily fully understand the calculus or the statistics, it will make sense. It does get a little calculus heavy later on, and I can upload these notes, but I'm going to try to just focus on the concepts here and what's happening. So essentially, because to start the statistics discussion, if we imagine we had some kind of monkey in a room and he or she was throwing darts at a dartboard or a wall, and we're assuming that the monkey is behaving completely irrationally with no rhyme or reason, the monkey will throw darts at random on either side of the wall. And it's impossible to throw darts outside the wall or on the ceiling. They only stick to the wall. And so if we define a coordinate system in which x is the horizontal axis, we are neglecting the y-axis because we're only dealing in one dimension right now to keep things simple, and we call the right side of the wall plus a, the left side of the wall minus a, and the center of the wall 0. If we take the distribution of points that are along this wall and map it to a probability distribution, what we find is that we can get some kind of value that looks like this. And it just tells us that so this is our probability distribution. Psi is not a good example to use here. Rho is a typically better function name to use when talking about probabilities, but I'll get to that later. All this is telling us is that the monkey is equally likely to hit any point along the x-axis on that wall. And so if we would like to know if the monkey threw a dart at the wall, what would happen, no one can really say for certain where the dart's going to end up. But what we can do is we can average them, and when we find the average, in quantum mechanics we use these things called angle brackets, and these angle brackets define things that are referred to as expected values. And so the expected value is an integral, which I can go a little bit into later, but just to keep things concept-wise, concept-rich for the beginning, it's just telling us that if you, what's the average x value across the wall that you'll find the dart. And so in this example, the most likely place to find the dart will be at x equals 0. And what we do next in statistics is we say, if we would like to know that one dart that the monkey threw, what's the average distance from the expected value that we get, we can define something called delta x, and I call it delta x sub n. The problem with using this value, delta x, is that it can take on a positive or negative value. Because the center of the wall we define to be 0. If the monkey throws to the right of the wall, we'll get a delta x value that is greater than 0, positive. But if the monkey throws to the left of the wall, we'll get a delta x value that is negative. And so if we average the delta value, the answer we get ends up being 0, which is not helpful to us. It doesn't tell us anything about how far away on average we're going to find the dart. And so what we need to do is square and then square root the delta x term. And so what that does is when we square a negative number, it removes the negative sign, and then when we square root it, it takes away the effect of squaring the number, so that we're just left with the positive value of it. So you could also think of square and then square rooting something equivalent to taking the absolute value of it. And when we take the average of delta x squared square root, that ends up being our variance, which we would call sigma in quantum mechanics and statistics. And that is the gist of the statistics that you will need to understand for working on kinds of problems where if you are given the wave function, psi, this symbol here is called psi. Psi takes on different cases, so it can be uppercase or lowercase. The psi that I have written here is lowercase, and it can, when you write a lowercase psi, it means that you are neglecting time, or you're assuming it's a time-independent Schrodinger equation. Schrodinger equation is the name of the model that describes the electron distribution, the function that describes electron distribution, or in this case, the dart distribution on our dartboard. And so if we wanted to find what our average or most likely x value is, we write it like this, and it is defined to be whatever you want to find the average value of times psi star, and psi star is its own quantity. It is the complex conjugate, I'll get to what that means, times psi dx. The complex conjugate of psi is necessary because when we deal with waves, because we are treating electrons like waves in quantum mechanics, you need to remove the imaginary terms before you can integrate them. And so when you multiply a complex number by its complex conjugate, you end up getting a real number that you can actually integrate. And the definition of the complex conjugate is all you do is if you see I, so I'll just write this out. So if we assumed psi had the form a plus bi, psi star would have the form a minus bi. And the reason for that is when we multiply psi and psi star, the i's will cancel out. So I'll just write this out. A plus bi times a minus bi. And this is an exercise in algebra. We would get a squared, which is a real number, plus abi minus abi minus b squared I squared. And so why is this useful? Well, this abi cancels, and if we remember the definition of an imaginary number, I is defined to be the square root of -1. So I squared is equal to -1. -1 is a real number. And so that is a good thing because now we can actually integrate this value. And so this is a real number, that's a real number. Our imaginary numbers canceled out when we multiplied our complex number, psi, by its complex conjugate, psi star. And so in this equation, once we plug in x and solve for it, we will get our expected value of x. I will go a little bit more into this later on in the video if you're interested, or if you're still watching, if I haven't bored you all to hell yet. And so the next thing I'd like to go over is what to do if you are given, so within the first few weeks of a quantum mechanics course, you're going to start seeing, or you'll be given wave functions, and these wave functions you will need to extract things from. So like in classical mechanics, when the professor gave you a position function over time, if you took the derivative with respect to time of your position function, let me just write this out, or I'll just talk about it because it's concepts. If you take the derivative of your position function with respect to time, you get the velocity function. And if you take the derivative of your velocity function with respect to time, you can find your acceleration. And from your acceleration value, if you know the mass of the particle, you can tell anyone what the force experienced on the particle is over time. And you can also go backwards. So if you're given the acceleration as a function of time and you integrate, if you're given boundary conditions, you can work backwards to your position as a function of time. And so you can tell me exactly what happens to this pen as it falls. And so that's why classical mechanics is so nice and intuitive to many people. Plus you see it every day in the real world, whereas quantum mechanics is something that we only see when you look at individual electrons or things that have such a small mass that we can no longer neglect the de Broglie wavelength. And so if you are really interested in quantum mechanics, the go-to book for colleges at UC Berkeley, we use this book by Griffiths in its Introduction to Quantum Mechanics. This is the 2nd edition international because I am poor, but it is a good book to read, and I believe he does a great job explaining stuff. Even if you're not a physicist, he explains it in a language that I think many people can understand. Someone like me can understand it. But there is a problem in it, 1.17, so chapter 1, that I think is very good at if you're interested in applying what I'm about to talk about with operators to wave functions. And so getting onto the discussion with operators, finally, the whole purpose of using operators in quantum mechanics is to extract observables from psi. And so psi had an analog in classical mechanics of x of t. So it's like x of t, except x of t is a precisely defined function. Psi is not. Psi can change over time, and it is not a precise value. It just gives us this probability distribution. And so you cannot simply take time derivatives. You do take time derivatives of psi, but what you get out are not precise values. They are also probability distributions. And the intuition behind that is, if you don't know precisely where a pen is falling through space, if you don't know precisely where an electron is, how are you going to be able to tell anyone precisely what velocity or momentum it will have or kinetic energy it will have? And so what we use are operators. And operators are the analog to classical mechanics, the d by dt, the time derivative. And so an operator by itself means absolutely nothing. An operator requires to have some kind of wave function or a function to operate on. Otherwise, it's meaningless. It's like, if we draw a biology analogy, it's like having an enzyme, but without substrates. The enzyme's just going to sit there and not do anything. It's not going to make any products. It's not going to tell you anything. So if you need to have an operator you need to have something to go with your operator to get anything from it. And so in quantum mechanics, one of the first operators you derive is the momentum operator. And it's a pretty long and tedious derivation, for me at least, because I'm new to physics, or new to quantum mechanics. And also, it's typically something that you can just look up. It's tabulated. And so the momentum operator, so momentum in physics is commonly called the variable p, and when you put a little hat over it, it makes it into an operator. And the value of p is just minus I h bar d by dx of psi. So minus I, that refers to the imaginary number. I is the square root of -1. H bar refers to Planck's constant divided by 2 pi, which is a constant. And d by dx is another term. And so the order that you place operators in is very important. So only this term right here is p hat. So p hat needs to act on something. In this case, it's acting on psi for us to get anything from it. And so why do you need to care about operators? So if you've been given a probability distribution or a wave function, and you want to tell someone what the expected momentum value of an electron is, that is described by the Schrodinger Equation, the wave function, you can do that by evaluating the average value of momentum. And so it's written as that with the angle brackets p hat, and what it means is that you take psi star, complex conjugate of psi, and then you have your momentum operator operate on psi, and that tells you what momentum you can expect for your electron. And up here, when I was defining what expected value of x is, you can do that because x does not have it, does not depend on the order. So I could have placed x here or here or here. It wouldn't have made a difference. It's the commutative property of multiplication. But operators, the order does matter. So within this integral itself, you cannot just put if you put your operator here, you would get a different value. Your operator needs to be sandwiched in between psi star and psi. So that's the reason why you need to put it here to get anything meaningful from your equation, because this d by dx term acts on the function that is directly next to it. You want d by dx to act on psi. If I put p hat over to the left of psi star, it would instead be acting on the complex conjugate of psi, which isn't necessarily what we want. And so to go through a problem, I'm not going to spend too long on this, so you can read through the math, but let's just go over it. In Griffiths 1.17, they tell you what your wave function is at time equals 0 and any x value, how likely. So this is your wave function. It does not necessarily tell you how likely you are to find anything at that certain x value. You need, because psi can take on negative values because of these complex elements that are part of it. And so the next step here is to, given what psi star is, determine what the normalization constant A is. And so in this case, capital A is a constant, little a is a constant, x is a variable. Psi, as a function of x at time equals 0, is a piecewise function on the interval from negative a to a, just like in our dartboard example. We know what psi of x at time equals 0 is, but everywhere else we're assuming you will never find x. And the first step towards solving your expectation values to get meaningful data is to determine the normalization constant A. So A is this constant that resides outside of here, and by definition, going back to the statistics part, any probability is a value between 0 and 1. And if we have a probability distribution, psi star times psi is a probability distribution. If you integrate over all space, you must get 1 as a result. Because if you have a particle, your particle must exist. If this value did not equal 1, it would be nonsense. And so to determine what your normalization constant is, we're going to apply this rule that tells us that psi star psi is your probability distribution, which you can sometimes write as rho of x, or it is written as rho of x. That must be equal to 1, and then it's just a matter of integrating and some algebra to determine what value big A must take on to make this a true statement. And so what we end up finding is that A must equal 15 square root of 15 over 16 a little a to the 5th power. The next step is to solve our expectation value of x. It's more integrals, so we plug in x times psi star, and the reason we can do this is because x is not an operator. We are only looking for the expected value, so we're only looking for expected value, so we don't have to worry about where x goes in here. We could have just as well put x there or x after psi because of the commutative property of multiplication. X is just a value. It's a variable, but it doesn't act on anything. And so we can evaluate this integral, and what we end up finding is that based on our wave function, we have our expected value of x at time equals 0 is 0. So that tells us the monkey throwing darts at the dartboard, the majority of the darts will land near the center of the dartboard. In the example, so this distribution probably looks something more like a sine curve than the constant value I had in the previous example, but I was doing that to introduce the statistics and try to keep things simple for earlier on. But you can just take this now, assume we have a different wave function, and we are now deriving all these other properties based on it. So the next step, once we've determined what our expected value of x at time equals 0 is to find what our expected momentum value is. And so in quantum mechanics, we can either write angle brackets p or angle brackets p hat. They mean the same thing. It is essentially evaluating the average momentum the particle will have based on its wave function. And what we end up finding is that our expected momentum value is 0. That's not to say that all particles have 0 momentum value. Some may have positive, some may have negative, just like some darts may have landed to the left, some darts might have ran to the right, an equal number of them on average, so everything cancels out. So the interesting thing comes in when we square our x value, when we evaluate the average value, the expected value of x squared. When we plug this in, we find that our expected value of x squared is actually a squared over 7, which is a bit confusing because our expected value of x was 0. And so the reason for that is because once you squared it, it doesn't matter whether or not it falls to left or right. If it takes on a negative value, that negative value will be squared and becomes a positive value, which is useful for determining what our variance is. Our variance is our sigma value that we talked about earlier. The next step is to evaluate the expected momentum value squared. And so when we do that, we find that our expected momentum value squared is equal to 5h bar squared over 2a squared. So also not 0 for the same reasons that x squared was not equal to 0. And so from this information, we can determine our variance or uncertainty of our position values and our momentum values. So from the last part that we just found, we found that the expected value of x squared was a squared over 7, and we found from one of the first parts that our expected value of x was 0, and squaring 0 is 0. This tells us what sigma of x squared is. So sigma squared x, this is a definition. This tells you what your variance is. It tells you what your standard deviation is. So away from your media, their expected value, how likely is the particle to fall a certain distance away from it? So it's essentially, think of like a Gaussian distribution like this. This would be your expected value of x. And then what you will find is that there's an average distance between your expected or average value and another particle. And this graphically is what sigma of x is. If sigma of x was 0, your probability distribution would just be a straight line like this because there's no deviation from the expected value. And then you can have very broad deviations in which you will find that your sigma variance or standard deviation value is a lot bigger. So bigger sigma values correlate to fatter distributions on your Gaussian. Gaussian is just the name of this bell curve. I wish I knew that when I took quantum mechanics the first time because I kept going over my head. But yeah, so Knowing what sigma of x squared is, we can calculate what sigma of x is. And we find that our standard deviation will be a squared over 7. A can be any value. And we can do the same for our momentum values. And what we end up finding is that when we multiply our variance in x, the variance in position, times the variance in momentum, it ends up being greater than or equal to h bar over 2. So our variance in momentum was the square root of 5/2 times h bar squared over a squared. And when we multiply these sigma x times sigma p, our a's cancel. So what that means is a can take on any value in our wave function, and what we are left with is that sigma x times sigma p is equal to h bar over root 7. So this was what x reduced to, and this is what the variance of momentum reduced to, and we end up finding that that is equal to 0.6 times h bar, and the Heisenberg uncertainty principle, this tells us that we must get a variance value greater than or equal to 0.5 h bar, and so we just proved it. So conceptually, what is the Heisenberg uncertainty principle? What it tells us is that the better we know something's position, the less well we will understand its momentum. And the example that they use in Griffiths is a very good one in my opinion. What we talk about is pretend you have a rope that's attached far away, and you are oscillating the rope like this. So the rope is behaving exactly like a wave. You can tell someone exactly what the wavelength is. And in fact, what else you can do is you can average over a bunch of wavelengths. Wavelengths to get an average. You can average over a bunch of waves to get an average wavelength. So you can be very accurate in telling someone what wavelength your wave has. But when you do this, if I asked you to tell me where is this wave, it is impossible because your wave is everywhere. So in this case, sigma lambda is very close to 1. Sigma x, your position of your wave, is essentially equal to 0. No idea where it is, and I should probably call this an approximation as well. So this is a rule with any wave. You can tell someone with certainty where you can tell someone with certainty what wavelength it has, but you do that at the cost of giving up the ability to tell them where the wave actually is. And so the converse of this is if you instead sent a pulse through your long rope, you can tell someone with a reasonable degree of certainty that where your wave is. So in this case, sigma x is about equal to 1, but you do that at the cost of throwing away your ability to accurately measure the wavelength. And so if your wave was like this, you're losing your ability to tell someone where your wave is now, but you can define more accurately your wavelength, but at the expense of giving up your ability to define the wave's position. And so this is a fundamental property of physics to all waves. The better you know the position, the less well you will understand its momentum, and vice versa. And you can apply the same thing to the time interval and energy variance, as I talked about in the previous video, in which you will understand the smaller you make your time interval, the greater the energy variance you can have, and a result of that is the creation and annihilation of virtual particles, which is some pretty far out stuff. So I hope this video was useful, and if any of you made it all the way to the end, I thank you. I know this stuff can seem very dry and boring sometimes, and it is a lot of math, but I think it's some pretty cool stuff, and on the surface of it, at least, quantum mechanics is a very interesting subject. Even if you hate it, you cannot deny there's something to it that is beautiful. So thank you for watching, and take care.